Thanks a lot for the introduction. Thanks to the organizers, Alex, and for inviting me and giving me the opportunity to talk. All I'm going to talk about is joint work with Stefan Kebekus and Thomas Fittanel, all varieties, everything will be over the complex numbers. And so vector bundles will appear through discussion of characteristic classes and maybe also, not some combinatorics, but okay, it's about projective space, which is an interesting variety. And so the motivation comes from a very old, beautiful theorem of Goethe, actually from 1957, really amazing, which says that if X is a smooth projective variety, not of general type, this assumption, and I assume that X is homeomorphic to projective space, so n-dimensional smooth projective variety homeomorphic to projective space, then as X is actually biregular or biholomorphic to projective space. So this can be seen as a statement saying that on the topological manifold, which is projective space, there is only one complex structure making this a smooth projective space. Yeah, and so this not of general type was necessary at the time. It was clear, however, from the principle of Goethe that if it's of general type, the canonical bundle has to be ample, and you satisfy equality in the Miao-Kayao inequality. And then, of course, the theorem of Yao, proven later with analytic methods, tells you that if you, in that case, you're a ball quotient. And you use that big theorem just to say, well, a ball quotient has pretty big fundamental group, and hence it's not Pn. So it's a little bit embarrassing. You put in all the theory, analytic theory of Kähler-Einstein metrics in the Kx ample case to find potentially a ball quotient, and then the only information you use is that you have pretty big fundamental group and it's not a trivial fundamental group to exclude the case. So in principle, you could erase that statement, but it's not due to Hirzebruch and Kodaira. And so the proof is really, really beautiful. One should look at it. Let's put a few ingredients. And you will immediately see why this was a paper written by Hirzebruch and Kodaira. So the first ingredient is Riemann-Roch in a form which is really amazing. So usually, even if you don't remember the general Hirzebruch-Riemann-Roch theorem, you know that it involves usually some Chern classes and some Todd classes of your variety. But then, with some magic concerning characteristic classes, you can write it in the following form. So if X smooth and D is a divisor, smooth projective D a divisor. Let me see whether I have enough space here. So then you want to write the Euler characteristic, and the way you write it is as follows. It's a sum over R plus 2S equal to N. Then we have C1 of D first Chern class plus 1/2 first Chern class of X to the power R, normalized by R factorial, and then we have A hat S, and then P1 up to PS, and then okay, you have with the fundamental class. So let me explain what the terms are here. Okay, first Chern class of D, first Chern class of X. So as an algebraic geometer, you're happy just first Chern classes appear, and that's the magic of this formula. And then I will use this in a second. What are these? What is this? This is the A hat. This is the A hat genus. You think about this is just a polynomial in where you plug in certain classes. And what are these classes you plug in? Pj in H4j of x with values say and r. What are these? This is the J von Triangel class. Several ways to subscribe. What name von Triangel class of the tangent bundle. So what is this? This is you take so Pj of x is nothing but -1 to the j, and then you take p to the 2j, so the Chern class of which complex vector bundle you take the tangent bundle of x as a real manifold. So let's write maybe like this, and then you complexify and you evaluate the Chern class. Okay, so this involves in some sense the complex structure of x, but only in a very weak way. And okay, we will see why this is so important to write Riemann off like this. So this is the first ingredient, together with the second ingredient. So the second ingredient is von Triangel classes. Are actually homeomorphism invariants.
Sorry, a naive question. Von Triangel class is related to usual chain class of complex tangent bundle.
Yes. Okay. You can imagine if this is the complexification again, you will get Tx plus its conjugate, and then you can evaluate the Chern classes on that, and you get formulas in terms of the usual Chern classes. So I will write the formula for P2 and P1. Yeah. So this is some linear combination of Chern classes, which then turn out to be homeomorphism invariants. So at the time, you see, so somehow this involves, I mean, this is even, so let's say this is a diffeomorphism invariant somehow, maybe, of the tangent, the real tangent bundle. But I mean, in the end, it's a homeomorphism invariant. Right? Novikov? That's Novikov, yes. Exactly. Okay, so now you see how you can go to business. You have something here where this is a homeomorphism, and this is just some combination of these. So this will be not change under homeomorphism. And then what is left is d and x, and you can try to control the chi. Yeah. So this is what you do. So first you argue that the car rank of x is 1, so there is only one chunk, one line bundle, so generates the car group. Since it's projective, there will be an ample generator, which we call O of 1. And then you use this formula together with a lot of more tricks and vanishing and so on to control chi of x comma O1. Okay, and then what you do, so this means, so this is not the whole proof, yeah, I mean just the control chi x of O1. And then with some vanishing, we control H0 of this bundle. Yeah, so that's now where algebraic geometry, okay, this is also algebraic geometry, but it's some pure algebraic geometry starts. And then this is some of the third ingredient, which I put here on my slide because I will use some variant later. So this is now another very, very classic, somewhat beautiful theorem by Kobayashi and Ochiai, or Fujita in the generalization, which is some of the start of the junction theory, where you try to characterize polarized varieties. Yeah, so you start with a polarized smooth projected variety, means you have a polarized variety together with an ample line bundle L. Yeah, and you want to study this pair, and especially you want to characterize special pairs. For example, Pn with O1. And this is one of the first theorems. So either you assume smooth or Combinatorial. You assume that L has the top intersection number 1, and you have at least dimension plus x dimension x plus 1, so n plus 1 sections, then actually x comma L is Pn comma O1. And the proof of this is very classical pure algebraic geometry. You look at the map associated with L, it maps to projective space. You see it has to be finite. And then because of the intersection number, it has to be 1 to 1, and you're almost done. Yeah, so this is now a very classical, purely algebraic geometry argument, which you can extend to the cone-Macaulay case from the smooth case. So this is somehow how roughly the proof of Hirzebruch-Kodaira works. They don't cite this result. Somehow there is an argument similar to what is now known as Kobayashi option. Okay, let me stay with this sort of argument for a little bit, because especially Fujita has pushed this approach of trying to recognize special varieties or polarized varieties much further. And this is what we will use later, because as we see, okay, can I move forward? Can you move forward once?
Oh, does it work?
Can you move? No, can you move forward one slide? It doesn't work. Ah, okay, here it is. Okay. So the question is, how do you put yourself into this Kobayashi-Fujita situation? So the following, which I call theorem Fujita 1, goes one step back. Yeah, so it starts again with an n-dimensional projective variety, with rational Gorenstein, especially in particular when they call it singularities. Now you assume that X is Fano, so that minus the canonical bundle is ample, and that the Picard roof of X is just generated in one. So then you know that minus Kx is an ample bundle, so it is some power of this generator. Yeah, so minus Kx, Ox minus Kx, is Ox of I for some positive I, just because there's only one line bundle, and then minus Kx is ample, so it's a power of the one ample bundle that we have. And you call I the index, and then the philosophy is to somehow classify by this index. And the philosophy is the higher the index, the more special the variety should be. So the more divisible minus Kx is in the Picard group, the more special your variety should be. So the more positive you can say minus Kx is, the more special it should be. And the first, is, as usual, is an inequality bounding this from top. So A, the index is always smaller than or equal to n plus 1. And then you can characterize the extreme case, and not just the extreme case, but you can start from the top and go down. So if I is equal to n plus 1, then you're already on projective space, even though your variety in the beginning was assumed not to be smooth, maybe. Yeah, but the idea is similar. You know, use vanishing theorems and so on to eventually go to the proposition where you have the sections, and then you have a map to Pn, and there is no other chance than this map being an isomorphism. But the interesting thing is that also if the index is almost maximal, if it's n, then X is isomorphic to quadric in Pn plus 1. Maybe include that n is 1 to distinguish it from the first case. And so this is a prototypical result from what is called adjunction theory. And then Fujita has pushed this one step further, and that's my last thing I'll do on the slide. You can now you understand the maximal case index n plus 1. You understand the submaximal case index n, and now you can go one step lower, which is index n minus 1. And now it gets interesting also from the point of view of rhetoric geometry or explicit birational geometry. You can show by looking at the section ring of the anticanonical how it is generated and in which degrees how the relations are generated, and you prove that in this case X is bi-holomorphic to a weighted degree 6 hypersurface in weighted projective space with weights 3, 2, and then as many ones as you need for the dimension. So there is some sort of toric geometry in the background, at least you embed into this weighted projective space, and the way to do is to really look at the section ring of this minus kx and how it is generated and how it looks. Okay, so this is somehow an interlude, it seems, that somehow starting from this homeomorphism problem, you move yourself into an algebraic geometry situation where you look at Fano varieties, say, where the divisibility of the canonical or anti-canonical plays a role, and you can play this game, say, until I equal n minus 1. There are some results for I equal n minus 2, but it's not so clear anymore as presented here. Okay, so this is the situation for smooth varieties, and also I can use. So now, for the rest of the talk, I will be interested in singular varieties. Okay, there are a lot of reasons to do that, but let me just mention cartoons now. X projective Kawamata log terminal variety homeomorphic So the natural setup would be a finite quotient of Pn by a finite group, but let me do the Pn case, which is somehow the interesting one, and the finite group can be dealt with later. And I want to understand what can X be like. And so maybe some words of motivation why I work with Kawamata terminal varieties, depending on your background. There are many, yeah. So either you come from the minimal model program where these are the singularities which appear on minimal models, or you discuss moduli of Fano manifolds, and you want to compactify the modular space of K-stable Fano manifolds of some fixed volume. At the boundary, you will find Fano manifolds with Fano varieties with KLT singularities. If you study actions of reductive groups on modules or vector spaces, and you take the invariant theoretic quotient, this quotient will have singularities in general, and they will be KLT type. So they will be in this class, or for example, you study toric, any toric singularity will be of KLT type. So a huge class, very natural class, you can arrive at this from many different perspectives. So what is the main problem? If I look at Kodaira-Hirzebruch, so the main problem is the formula here. Okay, we know Hirzebruch-Riemann-Roch on singular variety, but okay, the characteristic classes involved are some version of homology Todd classes or whatever. And the problem is that the tangent bundle does no longer exist. Yeah, it's a sheaf, complex coherent sheaf. You cannot use classifying spaces. The characteristic classes are produced in some other way, and there are some topological versions. There are some holomorphic versions. Sometimes, there are 2, 3, 4 incarnations. Some of them coincide. But in our case, all the numbers or the objects that appear in this formula exist, but you don't know whether there is an equality between the two sides, and it's very far off. Yeah, so we talk to people in this business, it's just not anything they can deal with at the moment. Okay, so we need some other methods, and I will just start somehow with some observations and walk through it, how you would approach the problem if you're given a projective KT variety which is homeomorphic to P. So what can you learn about this variety? And you can learn surprisingly many things just from going slowly and just think about what you're given. Okay, so I will start with this. Yes.
So did you say Herzebrück-Riemann-Roch does not help in Herzebrück-Riemann-Roch in the case of singular, in the singular case does not help?
It will help somehow. I will maybe I will ignore the threefold. I mean, for threefolds you can do it where you write it in terms of shell classes. I mean, for example, this formula does not exist. And okay, so the problem is what are the combination of your characteristic classes, however they are defined, which are actually homeomorphism invariant. Yeah, I mean, completely unclear whether anything should be homeomorphism invariant.
Is there a version of Grothendieck Riemann-Roch that might help?
There is, but it involves, I mean, that involves chi, and then you have some sort of some version of Todd classes. Again, even there is a choice, but because our varieties have Dubois singularities, I mean, some of them coincide. But okay, not clear how you exploit the fact that you know something like homeomorphic to Pn. So all of these massively involve the complex structure, and here somehow the magic of this formula is that the complex structure has been pushed only in these two terms, and they are only C1s. And as a birational geometer, you're happy because C1 is what you can do. Yeah, C2 is already interesting, and we will do it. And okay, so some observations about a variety homeomorphic to Pn. So let X be KLT homeomorphic. Okay, for those of you who don't know KLT so much, I mean, I will explain some of the major properties and in this sheet. Yeah? So I claim that A HQX OX will be 0 for all Q starting from 1. B, so this has, I go until M. Yeah? So, okay, first class map from X to H2, which is Z because it's homeomorphic to En, is an iso. C, the singular set has codimension. So KLT varieties are normal, so it has codimension at least 2, but I can gain one more thing. Codimension at least 3. D, for all Q between 0 and 4, and that's where our limitations of the methods come from. If I take the topological cohomology, so let's say my coefficient here is Z or Z2, I look at the restriction map from X to the regular locus. This is an isomorphism up to degree 4. So this looks still topological. Now comes a very interesting algebrogeometric property. X is factorial. Yeah, this means every Weyl divisor on it is Cartier. Yeah, so in particular, the canonical divisor is Cartier, which together with KLT, which implies rational, implies that X is Gorenstein, giving you circularity. And then, if this is easier again, Kx is either ample or anti-ample. So this means minus kx is ample so far. Okay, so these are the statements I will spend most of my time moving on. And so we can switch on the map.
Is it obvious that X will have to be projected?
Sorry?
Is it obvious that X will have to be projected?
Ah, sorry, did I not? I forgot. It's not obvious, so I have to assume. Thanks. No, I don't want to.
It is written on the left.
Yeah, so I just forgot to. But no, this is the. So I mean, here's of Kodaira works for compact scalar manifolds, which then quickly turn out to be projective. So I don't want to enter this, and I think it's. I will not comment on non-scalar geometry. Yeah, so okay, Z2 means what 2Z. So the reason is I want to discuss Stiefel-Whitney classes which live there. Yeah.
That's 4.
Oh yeah, sorry, it's 4. Yeah. So these two groups are okay. Other coefficients would also be okay, but I mean, this is matters. Here. Okay. So I start with this proof. So X having KLT singularities, it's a deep but old theorem that these singularities are rational. Yeah, so these are rational singularities. And so for rational singularities, a little bit of the standard Hodge theory you have on projective manifolds survives. So for the experts, they are Dubois. So what it means is that, I mean, the whole game is you want to exploit topological invariance to say something about holomorphic invariance, right? Because you control the topology. Yeah? So you have HQ, P and C. This is the same as HQXC because they're homeomorphic. And then there is a natural map, say phi Q, to HQXOX. Yeah, induced by just the inclusion of C into OX. And if you're on a projective manifold, that's just the projection into the direction of this Hodge decomposition component. And the theorem is that this is surjective still for rational singularities. Yeah? So this is the Dubois property, maybe. So what does this mean? Okay, if Q is odd, this already says that okay, this is 0 because it's for Pn. So 0 surjects onto this, so this will vanish. So now for Q even, you are okay. So Q even is only slightly more complicated. Right? I mean, this is still one-dimensional in the Q even case, but there is something inside of it here. It's the corresponding power of the ample C1. But okay, you can imagine that this, under some Hodge decomposition of some resolution, will not land in this Q0 piece, but it's in the QQ piece. It's in the PP piece if that is 2P. So by Q has non-trivial kernel containing, namely, it contains C1 of O of A amp. And this also will show you that the even HQs with values in O will vanish. Containing yes, facts Q. Yes. Okay, so that's good. So then B, as you can imagine, now you do exponential sequence. The HQO vanish on the left and on the right of the C1. So that is consequence. So that is good because then somehow we are in a similar situation as somehow Fujita. We just have one ample bundle and we move. Okay, so C uses another property of KLT. So one thing to know is that KLT surface singularities are just finite quotient singularities. So on a surface, KLT is equivalent to finite quotient singularities, which by some Bertini theorem says implies that if you put down your variety to a surface, it will have finite quotient singularities. And so this means in codimension 2, your variety X will also have finite quotient singularities. So there exists Z in X of codimension bigger than or equal to 3, such that outside of this, you have finite quotient readable, I guess, singularities. Now comes something which I have not explicitly stated, but so we are in a situation which is somehow funny at first. A variety might be singular as a variety, but it's homeomorphic to Pn. So it's a topological manifold. And starting from dimension 3, there are even isolated singularities which are topologically smooth. Yeah, we always think about the surface case where you think, there is some local fundamental group which will appear once you have singularities, but in the starting from dimension 3, you have these examples, and we are in the situation where we are topologically smooth, but algebraically singular. But okay, what I said is the point that if you have finite quotient singularities, these can only be topologically smooth if the finite group is trivial. Yeah, so this means outside of this set, the fact that you're topologically smooth sets that these finite quotient singularities are not there. Yeah, so this is at this. So the relation is that a finite quotient singularity, if it's really a singularity, is not topologically smooth. Have a finite quotient things are not topologically smooth. Okay, so outside of this Z, you're smooth. Okay, that was the clip. Okay, D is somehow more interesting from the topological point of view would be, I claim that these restriction, homological restriction homomorphisms are isomorphic. And so for this, I use the question is what kind of homology theory best to use on this non-compact thing, and how to exploit that you have a topological manifold. Okay, the only thing I know about topological manifold is that Poincare duality holds. So you use a homology theory where this is built in, and that is Wormel-Moore homology. So use Wormel-Moore homology. So this is homology with locally finite chains. If you have not seen this, you can look in Fulton's book, 1901, which summarizes all the facts needed for this proof. So X topological manifold, so topologically smooth, implies Poincare duality holds, and hence for R equal to Z for Z2, I know that there is a relation to standard cohomology. So the corresponding duality shift so this I mean by this theory has Poincare duality built in. And this tells you that in the non-compact case, it has to do with homology with compact supports. So this is minus Q R. Okay, and then there is a localization sequence, which is essentially the long exact sequence of a pair in homology. So you start with what you take away. So 2n minus q. So this a priori might be interesting because it's a singular space where you don't know that it's topologically smooth. And I have to mess up my mistakes. Okay. You get what you think you should get. You have this restriction morphism, and on both sides you get the homology of the complement. So this is the minus q. It's like and then you start again 1 degree lower. And you go on. So, but this is okay. So here is this restriction morphism, and so the interesting thing is that here on the left and on the right you have the homology of the singular locus, but you've just learned that the singular locus has codimension at least 3, which translates into the fact that okay, you can imagine that nothing should have homology in any sensible homology theory above the topological dimension. So these things will vanish in a certain range, and this will exactly be the range in my claim, so that for the low degree terms between 0 and 4, the restriction will be an isomorphism. So this is just with localization sequence and a dimension. And then you check that in this homology theory, it works as it should be. Okay. And now, so this is somehow all, okay, it uses machinery, but the arguments you do are relatively small. E I think is the most interesting part. So let me clean one board to be able to give the argument in one go. So let's try to remember when I erase, I will prove that x is factorial, and then f is that somehow it can only be ample or anti-ample. So how on earth somehow should you get something like factoriality, which is also a statement about the singularities, from the topological assumption? And as I said, this part I like a lot. It's a little bit more complicated than the previous parts. Okay. So yes. I have to write diagrams. Okay, if I think about devices and line bundles, I should write exponential sequences. Everything is in the analytification of x. I will not write this. So I write the two exponential sequences for x and the regular part. Now this will take me a little bit of time. Yeah. And then we go on. Then you write the restrictions. So far, nothing has happened. Just exponential sequences. So now I fill in what I already know from parts A to D. Yeah, so this is the standard thing. Now I will write out what I already know. So I'll put this here. So by topology, so this is 0 because it's 0 on Pn. And I know the restriction homomorphism is an isomorphism up here, so this is also 0. So I write two zeros on the left. Okay, so next thing. I said that I proved in the first step that there is no HQOX for any Q. So here I have a 0, and here I don't know. Zero. Okay. You agree that the difference between a Weyl and a Cartier divisor is essentially in this map. Yeah? Whether anything that is a Weyl divisor, so a Cartier divisor on X vec, actually comes from a line bundle on the whole thing. Okay, now here I know I have isomorphisms by the exponential sequence argument in part B. The restriction on the topological level, I'm still in Q less than 4 is still an isomorphism. And then I vanish again. Okay, snake lemma. This is so now I'm in a situation where I have snake lemma. So I imagine completing the things and going along like this. So I see that this quotient here, which is of interest to me, is isomorphic to this thing. So snake lemma says pick x y modulo pick x is isomorphic to H1 OXY. Okay, so now you think, how should I control this? Yeah, but now this here comes with another restriction homomorphism. And now you do commutative algebra, local cohomology of the stars. Ux has KLT singularities, and I said already that this means it has rational singularities. So these are Cohn-Macaulay, which say that certain local cohomology groups will vanish. And since the codimension of my singular set is 3, and my I have sort of Serre's condition as n, this will still surject. And this is 0. So this is somehow how you show that any divisor, which will give you a line bundle on x vec, will come from a line bundle on x, which is then the line bundle of the divisor on all of x. Okay, so this shows part E. As I said, this is the part I really like. And then the last part F is easy somehow. And so now you already know that your PK group is Z. Yeah, so there's, and somewhere inside of it is the canonical. So it can either be ample, minus of it can be ample, or it could be 0. Okay, my claim is just that it's not 0. Yeah, so the other cases I still leave in the picture. So if Kx is linearly equivalent to 0, then their duality, which I'm allowed to apply since my variety is Gorenstein, tells me that Hn of Ox, which is by Serre duality H naught of omega x, but now I assume that this is 0, which is H naught of Ox, is non-zero. But in the first step, I said that this Ox has no cohomology. So this case cannot occur. Yeah? Right, so here is a non-trivial step because you do Serre duality, which you can only do in this last step after you know that your variety is Gorenstein. So in this naive sense. Okay. So this was somehow the main technical, local also thing to be done here. And so I want to emphasize that okay, the approach here was completely naive in some sense. You think, okay, what am I given? What can I say? And you analyze it. So the next step involves characteristic classes. And so while there is an elaborate theory of characteristic classes on topological or piecewise linear manifolds, here, because of what we already know, we get away with naive arguments. Okay, so this is sort of part B of the proof, and it analyzes characteristic classes. So we exploit this homeomorphism to Pn in a different way. So for this, I recall that this inclusion has complement of codimension at least 3, and that my restriction homomorphisms on the level of homology are isomorphisms until degree 4. So this means that I can define first and second Chern classes just by restriction from the smooth loop. Yeah, so I define Chern classes naively as just, so this is the part which is topological restriction R 2j inverse Cj, which is now a manifold exact, and this will live in H 2j x z for j equal 1 or 2. So this gives me first and second Chern classes. The first Chern class would be definable other way, but so now I define more classes. First Pontryagin class, just by pulling back from the smooth locus. Now this is in H4, so still in the region where I'm okay. And the second Peter-Whitney class, which is even smaller degree. Yeah, so this is in H2, X with values in Z2. Okay, now I come back to the question at the beginning. Is this expressible in terms of Chern classes if you don't like these Pontryagin classes? These two things, by Novikov, in the case of Pontryagin, or Tom, in case of Stiesel-Whitney classes, these are homeomorphism invariants. So what does this mean? This means that if I now rewrite them, as was indicated in the beginning, as combinations of Chern classes, I know that I know something about this corresponding combination of Chern classes just by looking at the n. Yeah, so I need some more numbers. Okay. So what do I know? So what are the important relations? They just follow from the smooth case, yeah, because now everything is pulled back from the smooth locus where I have vector bundles. I understand everything. I can compute these characteristic classes using connections or maps to classifying spaces or just the definition. Yeah, what is the first Pontryagin class? This is the second Chern class of the complexification of the tangent bundle. If you plug in the standard formulas for Chern classes, you see that this relation holds. So this means that this relation here is a homeomorphism invariant. This linear combination is a homeomorphism invariant, as is one of x, but not quite mod 2. No? Because this is the Stiefel-Whitney class. Okay, so what can I get from this? So now I write some formulas. So let's just call the canonical bundle OX of R. We know it's some power of the generator. R is non-zero. Then, just by looking at how these numbers work on the end, I get the corresponding relations on X. So if X is projective KLT homeomorphic to the end, then first formula is 2C2 of X is equal to R squared minus n plus 1 times C1 of OX of 1 squared. So this is just because I know this relation on Pn. And then second, R, this divisibility index of the canonical is congruent n plus 1 mod 2. Oh, okay, so these are two informations about these characteristic classes. And this is almost all I can get in the general case, which is not enough. So I think about some other formula or form involving C1 squared and C2. And so if you think about vector bundles, in order for a semi-stable vector bundle, the Bogomolov-Giesecke inequality holds. Yeah, and so this is what I will recall now and then exploit. So in general, recall if the tangent sheaf of some x is H semi-stable for some ample H, then 2nc2 of x minus n minus 1 c1x squared, these are just the characteristic classes of the tangent sheaf, times h to the n minus 2 is bigger than or equal to 0. So this is Bogomolov-Giesecke. Okay, now I throw everything together into one big pot to get two results that I can present. So two results you can get from all of this. So theorem 3 in our setup, homeomorphic to Pn, if x is not of general type, and so this implies that it is Fano, what we already know, then x is biregular to Pn unless Tx is unstable. So this would be then a case to be analyzed further with some techniques I could comment on. But this is one of the results we get. I will explain to you in the last 2-3 minutes how to get this, and then how to get an unconditional result in a dimension up to 5. The message is just we've collected enough information about C1 and C2. So this follows. Since it's not of general type, minus kx is ample, it's the only other possibility. Minus r is the index. So if Tx is semi-stable with respect to the only ample there is, then Bogomolov-Giesecke holds. Yeah, so this is this here. But then I have a relation between C2 and C1 omega 1 OX1 squared. So I plug this in. So plug in this relation to see that then I get n is smaller than r, which is minus r, which is I. But what is this saying? It says that the index is bigger than n. Yeah. So it has to be n plus 1, and then by Fujita's theorem, it has to be Pn. So essentially, this comes from as soon as I have Bogomolov Giesecke, I'm done. Yeah? By Fujita. Okay, so this could then be analyzed further. So in the last -2 minutes, I'll tell you what this says unconditionally in dimension up to 5. Because I cannot prove in general that this Tx is stable or semi-stable. You see, for a long time, this was a conjecture. Yeah? The Fano manifold of Pika number 1, you would suppose that Tx is stable, but there is a counterexample after 30 years of positive results. Yeah? So I kind of need to use it. Okay? So it's delicate. Okay? So what I can say is that even without this Bogomolov Giesecke, I always know, this is the result of U, that C2 of x times C1 of O1 n minus 2 is bigger than or equal to 0. So this is like a Miyaoka inequality, but for Fanos. And this translates into the R squared is always bigger than or equal to n plus 1. If I plug in the numbers. And with this, I get my final theorem, theorem 4. For x, as usual, not of general type. Right. If dim x is less than or equal to 5, then x is actually Pn. Okay, how does this work? Let's just do the case n equal 5. So this new inequality tells you that your index is at least 3, where 6 is you have 1, yeah. And so the second thing you know how the clarity of R tells you that in fact I is 4 or 6, where 6 is already Pn. So you have to exclude the case I equal 4. But I equal 4 is 5 minus 1. So you have this weighted degree 6 hypersurface in weighted projective space, for which you explicitly prove the Bogomolov Giesecke inequality. So you exclude the case. So if I equal 4, Fujita 2 tells you X is a weighted 6 degree 6 hypersurface, and then you compute explicitly using this knowledge Bogomolov Giesecke holds, and then as before you get a contradiction. So you get I has to be bigger than 5, which is it.